In this lesson, we're going to talk about the chain rule. The chain rule tells us how we can differentiate compositions of functions. This allows us to differentiate a very wide range of functions that we can encounter. For example, consider the function f of x equals 3 times the quantity 1 plus 2x squared, all together squared. If we differentiate this function using our known rules, we would first have to expand out the binomial and then use the power rule. So let's see what that would look like. So f of x would be 3 times 1 plus 2x squared times 1 plus 2x squared, which is what it means to be a square. Just multiply the thing by itself, which would be 3 times 1 times 1 is 1. I'm just using FOIL here. 1 times 2x is, 1 times 2x squared is 2x squared. Then plus 2x squared times 1. 2x squared times 2x squared is 4x to the 4th. So it looks like I would have, everything gets multiplied by this 3, so I'm going to write this as 12x to the 4th. 2x squared and 2x squared would be 4x squared, times 3 would be 12x squared, and finally plus 3. Now that it is expanded, we can find the derivative using the power rule. So the derivative's power rule, what we would do is bring the 4 down, multiply it against the 12, so that's 48x to the n minus 1 power, so to the third, plus 2 times 12 is 24, x to the first, and then the derivative of a constant is 0. So that would be my derivative. Now suppose that we had observed that f was a composition of functions and chosen a substitution for the inner function. So if I let u of x be 1 plus 2x squared, then we can say that f of the function u is equal to 3 times u squared. And that would be what we call an outer function, this 3u squared. Now, if we make a small change to the variable x, the effect on the function u can be measured through the derivative u prime of x. So making an incremental change in x makes an incremental change in u. But any change in u then will affect the original function f. So u is now the independent variable of f. And we can say that a change in the variable u can be measured through f prime of u. So making an incremental change in x triggers a chain of changes to occur, starting with u and then to f. So this is the basis of the chain rule, that things happen in a chain. If we think back to the linear approximation property of derivatives, small changes to f would be delta f is f of u plus delta u minus f of u. And that's just simply, if I'm considering f as a function of the variable u, then I can determine how much the function f has changed with increments of u. So it's just as we've written here, f of u plus delta u minus f of u. But with the linear approximation property, that can be approximated with the derivative evaluated at u times the incremental change delta u. And this was all covered in an earlier video, so if it's unfamiliar and you want to understand exactly what I'm saying, go back to that video on linear approximations or linearization, see what I was referring to here. It's all the same, except instead of using the variables y and x, I'm using f and u. Now, if that's true, then u is also a function of x. So if u is a function of x, then small changes to u would be measured through something like u of x plus delta x minus, whoops, I meant to write u there, u of x, which can be approximated with the derivative evaluated at x times delta x. And together, what that means is that increments to f, delta f, can be measured as f prime of u times u prime of x times delta x. And where I'm getting that is if, let me get a little more space here, if delta f can be approximated with f prime of u times delta u, and delta u can be approximated with u prime of x times delta x, then all I'm doing is taking delta u, which is this, replacing it in for this one. So that gives me, I guess I should be precise and say that's really just an approximation, f prime of u, and then delta u is u prime of x times delta x. And if you don't fully understand what my argument is here, that's actually okay. The important thing that I want you to understand is A, sort of an intuition as to where the chain rule comes from, and B, having an appreciation for how to evaluate derivatives using the chain rule. So let's go ahead and state the chain rule. So if y equals f of u is a differentiable function of u, and u equals g of x is a differentiable function of x, then y equals f of g of x is a differentiable function of x, and the derivative of f of g of x is f prime evaluated at g of x times g prime of x. And this is generally the rule that we use to evaluate derivatives using the chain rule. But there's another way of expressing it using the Leibniz notation, which is dy dx equals dy du times du dx. So let's go back to our problem from the previous slide and take a look at what this derivative would be. To evaluate this derivative using the chain rule, what I'm going to do is observe that I have this inner function u, which is 1 plus 2x squared. Now it's called g of x up above, but I'm going to stick with u for right now. That means that f of the variable u would look like 3 times u squared. Now, the derivative of f with respect to u is pretty straightforward. We do this outer function, so it's the power rule. So bring 2 times 3, which would be 6, so that's 6u. But the thing is, the chain rule says that's not finished. That's the derivative with respect to the variable u. If you want the derivative with respect to the variable x, what you have to do is find the derivative of the function with respect to u and multiply that by the derivative of u. Okay, so we've got part of this. The derivative with respect to u is 6 times u. U prime, so u is the function 1 plus 2x squared. The derivative of that is 4x. But the function f is stated to be of the variable x. So I need to go back to the original variable x. So this would be 6 times u is 1 plus 2x squared times 4x, which would be 24x times 1 plus 2x squared. And if you compare that to what we had on the previous slide, you would need to multiply the 24x in to see 24x plus 48x cubed is the same answer that we had before. Now, I know that the chain rule can be a little bit overwhelming at first, but here's what I want you to be able to do. So I have the function f of x, which is 3 times some inner function 1 plus 2x squared squared. So I want you to be able to identify what the inner function and the outer function is, so that when you do these derivatives, what you know to do is take the derivative of the outer function as you would normally. So bring the 2 down, multiply it against the 3. Evaluate that outer function at the inner function. So you leave this part alone for right now. Subtract 1 from your exponent. That finishes up the derivative of the outer function. But you can't take a derivative of the outer function without multiplying by the derivative of the inner function. So the derivative of the inner function is 4x. So that gives me 24x times 1 plus 2x squared. And that is the derivative. So you don't have to write out what your outer function is and what your inner function is. You just have to know how this process works. If you have an outer function and an inner function, do the derivative of the outer function first, leave the inner one alone, and then multiply by the derivative of the inner. That's what you need to be able to do. So to get good at that, to get good practice with that, let's do some examples. A. F of x equals 1 over x plus 1. So I want to find the derivative of this. I could use the quotient rule. That's fine. Sometimes students prefer not using the quotient rule, and that's perfectly okay as well. I am one that tends to avoid the quotient rule when I can. And you can here, because you can rewrite this as x plus 1 to the negative 1 power. So raising something to a negative exponent is the same thing as inverting it. So now the chain rule can apply. So to get the derivative, the inner function is x plus 1. So this inner function here is x plus 1. So what I do is the derivative of the outer function, so it's the inner function to the negative 1 power. So I'm going to bring the negative 1 down, leave the inner function alone, and finish out that power rule. So negative 1, subtract 1 from your exponent, negative 2. Then multiply by the derivative of the inside part, which is just 1 in this case. So my derivative here, without using the quotient rule, is negative 1 over x plus 1 quantity squared. B, y equals sine 2x. Okay, to do this, the inner function is 2x. So what I will do is take the derivative of the outer function, which is the function sine of u. So the derivative of sine is going to be cosine. So it's cosine of u, which is my 2x, then times the derivative of the inside part, which is u, so times 2. So we have 2 cosine 2x. C, y equals the square root of 3x squared minus x plus 1. Here again, what I would do is take advantage of being able to rewrite roots as exponents. Use the power rule. But there's an inner function here for this power rule. There's this 3x squared minus x plus 1. So to find the derivative, I do the derivative of the outer function, which is the square root. So bring 1/2 down, evaluate it at the inner function, subtract 1 from your exponent. So 1/2 minus 1 is negative 1/2. Multiply that by the derivative of the inner function. So 3x squared, its derivative is 6x. Negative x, its derivative is 1, well, minus 1. And then the derivative of a constant is 0. To clean this up, I'll put the square root in the denominator and make this 6x minus 1 over 2 times the square root of 3x squared minus x. Oops, try that again. Make it look a little nicer. Minus x plus 1. And I have one more of these. Y equals tangent squared x. So if I want to get the derivative of tangent squared x, what I need to do is rewrite this as the tangent of x squared. That's what it means to do tangent squared x. It's just a shorthand notation. So the derivative is going to come from the power rule. So I'll bring the 2 down, multiply by the derivative, multiply by the inner function, subtract 1 from my exponent. So 2 minus 1 is 1. Now multiply that by the derivative of the inner function. So the derivative of tangent is secant squared x. So 2 tangent x secant squared x. These examples lead us to some generalized rules for derivatives, which combine a rule that we previously learned with the chain rule. The first of those is called the general power rule. So if y equals u of x to the nth power, where u is a differentiable function of x and n is a real number, then dy dx is n times u of x raised to the n minus 1 times du dx. Or equivalently, n times u to the n minus 1 times u prime. However you want to think about this, it's just stating you do the exponent first, using the outer function as your exponent, do the power rule on it. Then make sure you multiply by the derivative of the inside part in the end. Let's see a few examples. F of x equals 3x squared minus 2x to the 4th. The derivative here, the inner function is the 3x squared minus 2x squared. Okay, let's see some examples. Starting with f of x equals 3x squared minus 2x raised to the 4th power. My inner function is 3x squared minus 2x. My outer function is the exponent, so I do the derivative by handling the outer function first. So bring the 4 down, leave the inside function alone, and subtract 1 from my exponent. But I have to make sure in the end I multiply by the derivative of the inside part, which in this case would be 6x minus 2. Now, for simplifying, everything is pretty well factored. There's no reason to expand this cubic out to a polynomial. Factored form is considered the simplest form. One thing you could do is there's a common factor of 2 between the 6 and the 2. You could bring that out and multiply it against the 4, so 4 times 2 is 8. and make this 3x minus 1. That would be the simplest form. B. G of x equals the cube root of x squared minus 1 quantity squared. In order to do this one, we will use the chain rule, but it's going to be easier if we start off expressing this as an exponent. So a cube root we can always write as something to the 1/3 power. Now since this is already squared, if I write something squared to the 1/3 power, that's the same thing as the 2/3 power. So that's where we'll begin. Now, in order to find the derivative of g, I'm going to use the general power rule. So 2/3 is my exponent. It's going to come out front as a constant multiplier. I'll leave the inside part of this function alone and subtract 1 from my exponent. But keep in mind, 2/3 minus 1 would be the same thing as 2/3 minus 3/3, and we would get negative 1/3. Then we multiply by the derivative of the inside part, which is 2x in this case. Now, simplifying, there's not a whole lot to do. One thing I can do is combine 2x and the numerator of the 2/3, so that would be 4x. And when I have x squared minus 1 to the negative 1/3 power, I can make that a positive 1/3 power if I put it in the denominator. And not only that, but at this point, I can go ahead and switch it back to a cube root. So I could either write my final answer like that, or since it's just to the 1/3 power, it might be simpler if I express it as a cube root. C, y equals 3x minus 1 over x squared plus 3 quantity squared. So here I have a combination of the chain rule and the quotient rule. So in order to work this through, here's what I would do. I would say y prime first would handle this outer function. The outer function is easy. The exponent is 2, so you bring that down and you multiply it by the inner function and subtract 1 from your exponent. So 2 minus 1 is just 1. I'll leave that alone. And then we multiply that by the derivative of the inside part. Now before I actually do the derivative, I'm just going to state to myself that this is being multiplied by the derivative, and then do it in the next stage of this process, rather than trying to do it all at once. Okay, now I'll come off to the side, start doing this quotient rule. Numerator is 3x minus 1. Denominator is x squared plus 3. 3x minus 1 has a derivative of 3. 2x for this one. These two corners have to multiply together first. Whoops, I don't need to go so far that I can't see my result there. Alright, so 2 times 3x minus 1 over x squared plus 3 times the result of the quotient rule, so this would be 3x squared plus 9. I went ahead and multiplied the 3 into that binomial, minus, let's see, this would be 2x times 3x, which would be 6x squared. 2x times negative 1 would be minus 2x. And that's over the original denominator squared. So x squared plus 3, quantity squared. Okay, then it looks like I can combine some like terms in the numerator. So 3x minus 1 over x squared plus 3. 3x squared minus 6x squared would be negative 3x squared. And then negative applied to that negative 2x would be plus 2x plus 9 all over x squared plus 3 quantity squared. This would be a fine way of expressing your final answer, but the denominators are the same for both of these fractions. You could put this over a single fraction bar and make it 2 times 3x minus 1 times negative 3x squared plus 2x plus 9 all over x squared plus 3 cubed. Now, that negative in front of the 3x squared, sometimes instructors want you to leave leading term coefficients, make sure they are positive. So possibly your instructor might want you to factor out a negative to make that happen, or ask you to try and factor that polynomial to see if it cancels with anything. But this is the derivative function, and everything else is just simply algebra at that point. So it's up to your instructor where the final answer is going to be for them. Next, f of x equals x squared times sine of x. So this is using the product rule. There, in this case, is no use of the chain rule. And here's why. So to do this derivative, the first function is x squared. The second function is sine x. X squared doesn't require the use of the general power rule. So when I go to get my derivative, I don't need a general power rule here. I can do the derivative of the first times the second plus the first times the derivative of the second, which is cosine x. So this would be 2x sine x plus x squared cosine x. So there's no use of the chain rule there. Next up, we're going to learn how to extend our trigonometric rules. Each trig rule that we have, so for instance, the derivative of sine, we know the derivatives of the outer functions. That's our general rule for differentiating trigs. What we need to do then is make sure when we differentiate an outer function that we multiply it by the derivative of the inside function. So when we write this rule for differentiating sine of u, it's cosine of u times u prime. Same rule as before, it just is multiplied by the derivative of the inside part. Derivative of tangent is secant squared times the derivative of the inside part. Derivative of secant is secant u tangent u times the derivative of the inner part. And then our counterparts, the cofunctions, same rules, just opposite functions and negatives. So we can easily extend all of our trig functions using the chain rule. So let's try some examples with those. So if y equals cosine 3x squared, then the derivative of y is going to be, so we do the derivative of cosine, that's negative sine. We leave the inner function alone, but make sure in the end we multiply by the derivative of the inner function. So this is going to be negative 6x sine of 3x squared. Next here, y equals tangent cubed of 4x. Now this one is a little bit more complex because it actually uses the chain rule twice. Let me show you how. So this is actually tangent of 4x. Whoops, forgot my x. Try again there. Tangent 4x cubed. Now when I do the derivative of that, the first thing that I have to handle is the cube. That's an outer function which uses the general power rule. So bring that down. So it's 3 times the inner function subtract 1 from your exponent. So that's 3 tangent of 4x quantity squared. Now that gets multiplied by the derivative of the inner function. Well, the inner function is tangent of 4x, which in order to do the derivative of that, I also have to use the chain rule. So this is going to be 3 tangent squared of 4x times, all right, now the derivative of tangent 4x. The derivative of tangent is secant squared, so I do secant squared of 4x times the derivative of the inside part. The derivative of 4x is 4. So in the end, I've got 12 tangent squared 4x times secant squared 4x. I'm giving you lots of examples in this problem, or in this video, but I am getting more and more difficult examples as we go along. Okay, here's another one. This one is going to involve the chain rule, but it's also going to involve the quotient rule. So the quotient rule is what we are going to begin with here. All right, so I start this box over here. Numerator is 3x squared. The denominator is the cosecant of 2x. Okay, now the derivative of 3x squared, I can just use the power rule to get that. That's going to be 6x. The derivative of cosecant is negative cosecant of u, go ahead and write that in, cotangent of u times du. So in the end I have to multiply by 2. Just ran out of space on screen. These two corners always multiply together first in the quotient rule. So the derivative of function f in the numerator is 6x cosecant of 2x. And then it's going to be minus the product of those other two corners. But since there's a negative, it becomes positive. So plus, let's see, 2 and 3 multiply to 6. Then I have x squared cosecant 2x and cotangent 2x. All over the original denominator squared, which is kind of nice because if you'll notice, in terms of simplification, and some instructors actually may think, hey, this is where I need you to stop because I just want you to show me that you can use the derivative rules properly. Other instructors might want you to go on and do all of it. So for those, I'm going to finish this up. There is a factor of cosecant 2x in each term of the numerator. There's also a factor of 6x as well. So I'm going to factor out 6x cosecant 2x from the numerator, which would leave me 1 plus x cotangent of 2x. And that's all over cosecant squared of 2x. But I have a factor of cosecant 2x here, 2 of them right there. One of those will cancel out. So it looks like I have 6x times 1 plus x cotangent of 2x all over cosecant of 2x. One last of these. H of x equals 2 cosine cubed of 3x to the 5th power. Okay, let's rewrite it. Make it 2 cosine of 3x to the 5th power. and I'm going to make this all together to the third. Okay. All right, so the outer function here, it is the cube, and therefore I want to use the general power rule. So bring the 3 down, multiply it against the 2, so that's 6 times cosine of 3x to the 5th power. Subtract 1 from the exponent, which gives me a 2. And then I multiply by the derivative of the inside part, which I'm just going to state here I will do in just a second. And that's just because I can see that this is going to require another iteration of the chain rule, so step by step is a good way to approach this. All right, so 6 cosine squared of 3x to the 5th. That's all finished for my derivative. What I need to come up with now is the derivative of cosine of 3x to the 5th power. And my outer function this time is cosine. The derivative of cosine is negative sine. So negative sine evaluated at 3x to the 5th. But then I have to multiply by the derivative of the inside portion. So times 5 times 3 is 15. Bring 1 down for my exponent, so x to the 4th. When all is said and done, 6 times 15 is 90. And then I have my x to the 4th. Oh, you know what? I should put that negative out front here. So let's make this negative 90x to the 4th. Then I have cosine squared of 3x to the 5th power times sine of 3x to the 5th power. And there's my final answer. In this next example, I want to differentiate the function f of x equals x squared times the square root of 1 minus x squared. Now, I have two functions that are multiplied together, so I am going to have to use the product rule. And another thing that's complicating this is that one part of those functions, the 1 minus x squared, which I could rewrite as 1 minus x squared to the 1/2, needs to use the chain rule, which it turns out this really isn't all that bad getting the initial derivative. It's the process of simplification that gets a bit complex here. Well, let's get started with the derivative first. So the derivative of a product, I'll take the derivative of my first function, so the derivative of x squared is 2x. And then I'll multiply it by the second function, so 1 minus x squared to the 1/2 power. And then it's plus the first times the derivative of the second. The derivative of the second, using the chain rule, I would bring 1/2 down, leave the inside portion alone, subtract 1 from my exponent, so 1/2 minus 1 is negative 1/2, and then multiply by the derivative of the inside part, which is negative 2x. So there's my derivative. It isn't simplified, but that's where we're starting. Now, to simplify this, what we would need to do is maybe begin with some simpler things. Like, for instance, multiplier of 2 and 1/2 would cancel each other out. That's no problem. I can, I'll leave this as 2x square root of 1 minus x squared. And then on the other side, this negative is going to make this a minus. And I'm going to put x cubed in a numerator, and then put in the denominator 1 minus x squared to the positive 1/2 power. Now, that gets me started. So the next thing that I need to do then is I'm looking at two separate fractions for which I can combine into a single fraction. That's how I'm going to get the simplified form of this. Now, they need to have a common denominator. So to get a common denominator, I need to have them both have a factor of 1 minus x squared to the 1/2 in the denominator. So effectively, I need to take this first term and multiply it by 1 minus x squared to the 1/2 over itself. And leave this one alone. Now, what that allows me to do is combine the terms 1 minus x squared to the 1/2 and this other 1 minus x squared to the 1/2. And what happens is something that's really nice, because these are effectively two square roots that have the same thing underneath the square root. And so we're effectively squaring a square root, and they become just 1 minus x squared. So now have 2x times 1 minus x squared all over, and actually, you know what, I'm going to go ahead and say minus x cubed. I'm just going to combine these as a single fraction now, and the numerator can simplify a little bit more if I distribute the 2x and make it 2x minus 2x cubed minus x cubed. The denominator is pretty simple already, but I'll go ahead and express it as a square root rather than to the 1/2 power. And lastly, I've got two like terms, negative 2x cubed and negative x cubed, which will combine. So that would give me 2x minus 3x cubed all over the square root of 1 minus x squared. And actually, probably would be simpler if I went ahead and factored an x out of the numerator. It's generally considered simplest if you're in factored form. But that right there is the simplest form of this problem. Now, in terms of when you need to simplify, generally it's not always. If you just need a derivative, really the very first part that we came up with right back here, that is the derivative, and you don't technically need to simplify it unless you have to do something with that derivative. Like if you need to set it equal to 0 to solve, you're going to want to make that thing simpler. If you're going to need to find a second derivative, you definitely want to make it simpler than that. So simplification isn't something that you always have to do. Different instructors have different ideas of when you should simplify and when you shouldn't, so always follow your instructor's last instructions on that. But this right here is how you would get the simplest form if you needed to. Now the next topic here, let's talk about what happens when we differentiate constant multiples of x. So consider the derivative of y equals sine 2x. We can find this derivative using the chain rule. So the derivative here is going to be the derivative of the outer function, which is sine, would be cosine. Multiply it by the derivative, or leave the inside function alone, multiply it by the derivative of the inside function. All right, then rearrange everything and make it 2 cosine 2x. Okay, so the thing is, this is only off by a constant multiplier of x. So it's just 2 times x instead of x. And what happens is you just follow your rule of the outer function and multiply by this constant. So if you want to speed things up, you don't have to necessarily do the chain rule for these kinds of problems, because you can generalize this. If you see what happens when you differentiate y equals sine of a times x, which would be any number times x. So the derivative would be derivative of the outer function evaluated at the inner times the derivative of the inner, which is a cosine ax. In that situation, if you just remember that it's only off by a constant multiplier, you can save yourself some time in coming up with derivatives. So for instance, here's a few examples. Y equals tangent to 5x. The derivative here, the derivative of tangent is secant squared. So it's going to be 5 secant squared 5x. So put the constant multiplier derivative out front, then just do the derivative of the outer function. So here, if I want f prime of x for cosecant 4x, so the derivative of cosecant is negative cosecant cotangent, so it's going to be negative 4 cosecant 4x cotangent 4x. And if you do the chain rule on these, that's perfectly fine. I'd much rather you use the rule to get the correct answer, but if you want a way of kind of speeding up things that you run into quite a bit, this is a great way of doing it. Here, y equals 3 cosine 2/3 x. Its derivative would be 2/3. All right, then we have the 3, so times the 3. Cosine is derivative that is negative sign, and it's going to be 2/3 x. 3's cancel. Looks like I have negative 2 sine 2/3 x.